Hello, friends. As you may recall, Christopher Nolan's 2014 picture Interstellar was a huge success. Wormholes, black holes, and extraterrestrial worlds were among the space-related ideas that were accurately and scientifically portrayed in this movie. However, the film's final scene was arguably the most frightening. Cooper, the film's main character, plunges into a black hole during the final scene. The black hole in the movie was called Gargantua. Cooper and his spacecraft plunge into the black hole. At first, everything around him was pitch black, total darkness. However, when he descends further, he spots some particles that look green. His spaceship is scratched when these particles strike it. His spacecraft caught fire, and there were several sparks and light bursts. After being ejected from his spacecraft, he continued to fall into the black hole. Abruptly, he was in a 5-dimensional environment, a tesseract in 5 dimensions. It was an experience beyond comprehension, a location where he could use gravity to connect with his earlier self. After seeing these scenes, you may have questioned whether it's indeed possible. Does a black hole involve this? What would we see if we fell into a black hole? Come, let's attempt to comprehend these elements in the video for today.
Black holes remained largely unknown until the 20th century. A black hole is a region in space where the force of gravity is so strong, not even light can escape.
From the outside, you can't tell what is inside a black hole.
Black holes haunt our universe, dark centers of gravity that swallow everything in their path.
Friends, let's start at the beginning of this story. Black holes don't have a long history. Black holes were unknown 100 years ago. Black holes were later found as a result of Einstein's theory of relativity. The theory is divided into 2 sections, friends. There are 2 different theories of relativity, the general theory and the special theory. Einstein explained how speed affects time in his 1905 special theory of relativity. Time will slow down for you if you are on a spaceship traveling at a very high speed, compared to those back on Earth who weren't on the spaceship. Because you wouldn't sense time slowing down in a spaceship, the word relative is crucial. It would seem as though time is moving at its typical pace here. However, you will discover that the passage of time was different when you return to Earth. This is known as kinematic time dilation. If you've watched my video on the time traveler, I've gone into great depth about how this operates. According to Einstein's general theory of relativity, time dilation can be caused by both speed and gravity. He came up with this in 1915. Time would seem to slow slower for you the more gravitational force you felt. Gravitational time dilation is the term for this. And Interstellar did a fantastic job of portraying this. 1 hour on the Aqua planet is equivalent to 7 years on Earth when Cooper and his group arrive. The planet was quite close to the Gargantua black hole, which is why this occurs there. Thus, time was affected by the black hole's gravitational pull. Einstein wanted us to picture a space-time fabric in order to visualize this. All planetary objects are arranged on it, much like a mesh. The mass of the items causes the space-time fabric to bend. Additionally, bending the mesh causes time dilation in addition to increasing the attraction of physical objects. Gravity also affects other types of energy, such as heat, light, or sound. Yes, exactly. Einstein also came to this conclusion. Nearly everything is affected by gravity. In addition to physical objects, the force of gravity also draws in heat, sound, and light. This implies that there may be objects in the universe with such a strong gravitational pull that they are able to absorb all light, friends. In the event that such objects exist, they would be entirely black. They won't be visible to us, because they are impervious to light. This is what black holes are, friends. However, the idea of black holes was just theoretical until Einstein introduced his theory of general relativity. Einstein was aware that light is affected by gravity. Theoretically, light-absorbing items were also feasible. However, Einstein was unaware of the existence of real black holes. In reality, Einstein thought the idea of black holes was strange when he was alive. He was aware that such things might exist in theory, but that infinity could also exist in theory. However, practically speaking, he didn't think that such things were true. Not even the phrase black holes had been coined by the time of his death. One of the main ideas of Einstein's theory was that gravity's power is limited by the speed of light. The speed of light is the upper limit of gravity's force, which we do not feel immediately everywhere. Using a real-world example, if the sun were to abruptly depart, we would discover this 8 minutes later on Earth, since it takes 8 minutes for sunlight to reach the planet. However, 8 minutes later, Einstein predicted that the gravitational effects of the sun's absence would also be felt. Isn't it fascinating? Carl Schwarzschild, Johannes Droste, and Subramaniam Chandrasekhar were among the numerous scientists who worked on the theory of general relativity after Einstein. After solving a number of equations and attempting to determine their solutions, it was theoretically demonstrated that objects such as black holes do exist. By the 1960s, scientists and researchers had finally come to the conclusion that humans will be able to observe black holes, not just theoretically, but maybe in the real world. Because these do exist in space. The term black hole was used for the first time by a magazine in 1964. But only after 1967 did the term gain popularity when physicist John Wheeler popularized it. The term black hole is misleading, despite the fact that it sounds quite dramatic. Black hole. It may seem as though there is a real hole there. However, that isn't true. The space has no holes in it. Stars are the source of black holes, thus it has some substance in the middle. However, the core of all stars, including our sun, is always undergoing a nuclear fusion reaction. Light and heat are the results of these interactions. In addition to the force of gravity at the star's core, the heat generated exerts an outward pull that keeps the star alive. This is how the stars maintain equilibrium throughout their lives. The forces pushing outwards due to the reaction, and the forces pulling inwards due to gravity. But these reactions take place when a fuel exists, either hydrogen or helium. The fuel wouldn't always be there. It would get burned up at some point. And when the fuel ends, there wouldn't be any forces pushing outwards. And the gravitational force pulling inwards wouldn't be countered by an equal force, so that star will collapse on itself because of its own gravity. This will take a long time, by the way. Our sun's life expectancy is around 10 billion years, but what happens next depends on the mass of the star. Let's look at the chart of the life cycle of a star. If the mass of the star isn't high, i.e., if it was a small or average-sized star, it becomes a red giant. It may then develop into a planetary nebula, or a white dwarf. However, a massive star with a lot of mass cools down and becomes a red supergiant when its fuel runs out. The supergiant then explodes and transforms into a supernova. A tiny core is left behind after this. It is referred to as a neutron star if its core is very small, and a black hole if it is larger. In essence, the star's mass becomes small and condensed after collapsing due to gravity, and it has the potential to become a black hole. In particular, how small is the compressed star's volume? If a star the size of our sun becomes a black hole, it will only have a diameter of 50 kilometers. Is it possible that the volume could get this low? The intriguing thing, though, is that our sun will not become a black hole in the future. Subramanian Chandrasekhar, an Indian-American astrophysicist, demonstrated this. The Chandrasekhar limit value was created by him. According to him, a white dwarf's maximum mass is 1.4 times that of the sun. It cannot remain stable above that point and would either become a black hole or a neutron star. However, since the sun, our sun, falls within this bound, let's now examine the nature of black holes. Black holes come in 3 or 4 main varieties, friends. The stellar black hole is the first. The most prevalent kind of black hole is that one. The black holes that stars produced. Between 10 million and 1 billion of these black holes are thought to exist in our Milky Way galaxy, according to scientists. The primordial black holes come next. The size of these black holes is comparable to an atom. However, their mass is comparable to that of a mountain. Their size is assumed to be as small as an atom. Friends, we don't know much about these black holes. They are just hypothetical. The supermassive black hole is the third kind of black hole. These are huge black holes. They are so large that their combined mass exceeds that of 1 million suns. Furthermore, it fits into a ball with a diameter equal to that of the solar system. Scientists think that every major galaxy has a supermassive black hole at its center. Sagittarius A is the name of the supermassive black hole located at the center of our Milky Way galaxy. Additionally, the Gargantua black hole in the movie Interstellar was described as a supermassive black hole. Scientists also think that a fourth kind of black hole might exist. The fourth kind of black hole will be an intermediate black hole, which is in the middle of the sizes of stellar and supermassive black holes, though this cannot be confirmed. However, no evidence of it has been found as of yet. According to your interpretation of the images you have seen thus far, and the movie Interstellar, The black hole is not a large black ball that takes in everything in its path. This is how the black holes appear. Since it is in high definition and more three-dimensional than the picture we took a while back, this is the black hole as it appears in the film. The orange ring that surrounds the black hole is the first thing you'll notice in this picture. We call it the accretion disk. It is a crucial aspect of black holes. As you are aware, black holes have extremely strong gravitational pulls. As a result, a large amount of gaseous matter and debris is drawn to the black hole and stays floating around it. In the same way that the sun's gravitational pull causes the planets to orbit it. The difference is that black holes have such a strong gravitational pull that objects revolve around them quickly and heat up to the point where they resemble flowing fluids. They actually turn into particles that resemble fire and have a temperature of over 1,000,000 degrees Celsius. They orbit the black hole more quickly the closer they come to it. The particles begin to glow because they are rotating so quickly that they rub against one another and become compressed. X-rays are the primary electromagnetic radiation that they emit. The movie did a great job of depicting this accretion disk. The only mistake was that it wasn't truly orange. X-rays are invisible to the human eye. X-rays were not part of the visible light spectrum. In order to represent it, we merely use an orange-yellowish color. This disk's true color would be more akin to blue. The first image of a black hole was captured in 2019. Even in this, the accretion disk was represented by the color yellowish-orange. The particles on one side are brighter than the other, which is something that is evident in the real image but may go unnoticed in the film. That has a straightforward explanation. We perceive particles spinning in our direction as being brighter, and those spinning in the opposite direction as being dimmer. The Doppler beaming effect is to blame for this. You can use this blurry image to determine the direction of the spinning particles when you see the actual black hole photo. The brighter area is moving in our direction, while the darker area is moving away. Returning to the movie's image, you'll also notice that the accretion disk creates an optical illusion as a result of gravity. It gives the impression that the black hole's top and bottom are covered by the disk. Light is bent by gravity, which is why it appears this way. The space concealed behind the disk. The light from the area must pass over it when viewed from the front because gravity bends it. The black hole will appear to be a typical round disk when viewed from above. Only when looking at the black hole from the sides does this illusion appear. In addition, you will notice a final circle of light as you enter the black hole. The photon sphere is what it is. This region has such high gravity that light begins to orbit the black hole. What constitutes light? Photons. The black hole is orbited by the photons. This implies that since light travels in a circle, creating a ring, it is theoretically possible to see the back of your head if you survive to reach this region of a black hole. The black hole's boundary comes after this point. We call this the event horizon because the gravity is so great beyond this point that not even light can escape. It is regarded as a boundary. Beyond this, everything is black. Theoretically, there is no chance of escape. If you are falling into a black hole and have passed the event horizon, how could a human get out of it if not even light could? Cooper's spacecraft continues to plunge into a black hole, crosses this event horizon, and then abruptly enters a five-dimensional space, as depicted in the movie Interstellar. This portion of the film is entirely fictional. We don't know what's inside the event horizon, so it's just conjecture. A physicist who had won the Nobel Prize was employed by the film's creators to ensure that everything was true to science. However, the film clearly shifted to the imagination for those scenes that dealt with topics that science has not yet discovered and about which we know nothing. What will be the black hole's center? This is what Einstein's general theory of relativity attempts to explain. According to this theory, the black hole's center is known as singularity. The area of a black hole where the curvature of space-time is infinite is known as the singularity. Remember the mesh I discussed in the first part of the video? The space-time mesh will bend more when the object is heavier. This is so twisted in the case of a black hole that it extends endlessly. According to the theory of relativity, gravity affects time, energy, and everything else. Time slows down infinitely as the gravitational force increases. However, what does an infinitely slower time mean? Does this imply that the universe outside would have ended for the rest of us if you were to enter a black hole and be able to escape? We're not sure. All we can do is speculate. What are your thoughts? Let me know by leaving a comment below. Some intriguing hypotheses have been proposed. According to one theory, light reflects off of the event horizon at several points before reaching the singularity, just as we cannot see inside a black hole from the outside because light is absorbed into it. Therefore, there is a chance that objects could be seen inside the event horizon. This single photograph is the only proof we have of black holes. This image was captured on April 10, 2019, by the Event Horizon Telescope. This practically demonstrated the existence of a black hole, roughly a century after their theoretical proof. One thing is certain: the gravitational pull of a black hole will probably cause you to break apart if you fall into it. In milliseconds, you will perish. Nevertheless, friends, you shouldn't be afraid of black holes. A common misunderstanding in the past was that black holes consume all matter, continue to grow, and ultimately bring the universe to an end. However, that isn't how it operates. As previously mentioned, every galaxy has a supermassive black hole at its core. Additionally, every other star and planet in the black hole's orbit revolves around it, similar to how every planet in our solar system orbits the Sun. Though in a far more potent way, the same thing occurs at the galaxy's center. In conclusion, you will be safe and secure if you keep a safe distance from a black hole and practice social distancing. Another intriguing idea is the 5-dimension concept that was discussed in Interstellar. Let's discuss it in a later video. For now, that's all. You can watch more space-related videos if you enjoyed this one. If you haven't already, watch the one about time travel. There, these ideas are thoroughly explained. Many thanks for watching the video, friends.